go. So we are looking at derivatives. Our goal here, thank you, is looking at this notation and understanding that this is just another way for us to identify a limit at a point or the slope of the tangent line. And again, this is from yesterday. This is the same thing that we did yesterday. The only added new thing is this word derivative, which means the slope of the tangent, which means the limit as h goes to 0 of this equation. Or you can use the other one, the limit as x approaches a, oh, I don't like my handwriting on this one. That's okay. Of f of x minus f of a over x minus a, which is the same thing as y is 0. Oh, whoops, not 0. Y minus y0 over x minus x0. All of these mean the same. They are the derivative, the instantaneous rate of change, the limit as x approaches our point of interest, or the limit as the change in the distance h goes to 0. All of these things mean the same. So in our first example, find the derivative of f of x equals x squared. In other words, find f prime of x. So we can use any of the points that, or any of the versions that we see. I don't have a point of interest, so I might as well just use this version here. And red is so aggressive, isn't it? Let's do a nice calm color. F prime of x equals x plus h all squared minus x squared all over h. Okay, so h is the distance between our point of interest x, which is a general point. Get off your phones, my friend. And the point of interest. So h is the distance. We're trying to let the distance go to 0. And I just noticed I forgot my limit symbol. Poo-poo, Miss Gordon. Limit as h goes to 0. This is a symbol that says we have not yet let the limit go to 0, but we're going to. So the limit as h goes to 0 of x squared, so I'm just expanding that bracket to xh plus h squared minus x squared all over h. I collect like terms. I see a positive x, I see a negative x, they cancel out. I see an h in all the leftover terms, so this cancels, this goes down by a degree. So my limit as h approaches 0 of this, the simplified version is 2x plus h. Now I take the limit. Take the limit means let h go to 0. This will end up being 0, so I can do this by direct substitution. So my derivative, f prime of x, is 2x. And I'm sure Mr. Monroe has been showing you all the beautiful shortcuts, which you will learn in the next unit. Or if you have learned them already, then this next unit will be super easy for you. All right. So this is the theory behind derivatives. How and why do those rules work? Because this is the theory behind it. We're looking at a point close to the point of interest, approaching it as close as possible, and looking at what kind of values we get out of it. So this is a derivative function, right? This is the instantaneous rate of change, instantaneous rate of change of f of x, the original function. Okay, so I can put in any x value, and then you will be able to know what is the slope of the tangent at that point. In example 2, we are asked two things. It says find the derivative and state the domains comparing f to f prime. So let's take a look at what is f prime first. F prime is the limit. And do we want to do the other one now? As x approaches a. Or do we want to stick with the H one? You want to stick with the H one? Sure. It's like a choose your own adventure today. As H goes to 0, square root x plus H plus 2 minus square root x plus 2 all over H. Okay, tell me some strategies. Rationalize, yes, okay, so let's rationalize the numerator. So we're going to do square root of x plus H plus 2 plus square root of x plus 2. And we're going to do the same thing on the bottom. It's H plus 2. Oh, this pen is terrible. X plus 2. Okay. So then on the top, I get x plus H plus 2 minus x minus 2. In the bottom, I get H times all the stuff in the brackets. I'm just not going to rewrite the bracket. But just know that this is the same bracket here. I'm not going to expand it or anything. In the top, positive x, negative x, positive 2, negative 2. I'm only left with a h in the top, which factors out of the h in the bottom. So then the limit as h goes to 0 is just a 1 on top. And then I have x plus h plus 2 plus x plus 2. Now I take the limit. Once I have simplified it, I'm going to let h go to 0, and there's only 1 in here. So I end up with x plus 2, both are radicals. So that means 2 times root x plus 2 in the denominator. Oops. X plus 2. This is f prime. This is f. Okay, so now what are the domains of these two? What is the domain here? What is the domain here? Let's do the original one first. What is the domain of the original function? X must be greater than or equal to negative 2 because we want positive numbers under the radical. What about the f prime function? X greater than negative 2. It should be equal. Ooh, why not?
You can't have a 0 in the denominator.
Yes, we cannot have a 0 in the denominator, so we have a slight change of plans when it comes to the domain. Okay, so f prime has a strict restriction, f has an inclusive restriction. All right. F prime of yuck. We are going to do it, but it's going to get ugly. It's going to get very ugly, but it will simplify to something pretty cute. Okay, so we got to grow through. Think of it like as a person. You start small and cute, and you go through puberty. You get really bad acne and really bad haircuts, and then you blossom into the person that you are always meant to be. Okay, so this is kind of the mentality we're going with. So, like I said, go through the pain, wade through it slowly. Don't freak out. Expect ugliness, but in the end, we're going to end up with something cute again. All right, so the limit as x approaches, I'm going to do it this way. It doesn't really matter which way you want to do it, but let's see here. X plus 1 over 3x minus 2 minus a plus 1 over 3a minus 2 all over x minus a. Okay, stacked fraction. You don't have to use my method. Would we like to just stick with the H version? If you can, if you want to.
But is it going to be different?
It will look a little bit different, the method, but at the very end, your answer should definitely be the same.
I'll try both.
You can try both methods if you like. I'm going to try this one. I haven't done this one in a while, so you choose your own adventure here too. Ooh, let's do the purple one. I like that. 3x minus 2, 3a minus 2. It's going to take us a moment, so bear with me with a moment of silence here. This way might be uglier because we don't actually have a point of interest. We're just using a general point A. It's not looking pretty, hey? I don't know. Lots of expansions, yes. But we're collecting like terms, right? Well, as soon as we expand the expansion, it gets really ugly, but then that's when things start getting pretty again, right? Sure. Let's see, 2x plus 3a minus 2. Hopefully you're seeing things that are canceling on your end. I'm going to leave my denominator factored to see if there's anything I can cancel out once I've combined my top. Hmm.
So there's no way this is right. I'm getting the limit is -5. Okay, good. Okay, good.
You got -5?
Yeah.
Okay. I'm still working on it. My brain is not as quick as you
Let
guys.
me try your method. Did you guys use the A method or H method? H method is easier, right?
The first blue one that I highlighted?
There's like 11 terms.
Okay, what did I do wrong here? X times 3a is 3ax. X times 2.
I'm gonna try the A method too. So, that's time effects.
Oh, I see what you're saying. This one here is just x, right? -3x, right?
Let me try it.
Yes, that is where my mistake was. That should be a -3x. Thank you for catching that. Okay, that makes my life a lot easier. There we go. I was wondering what was going on there. Oh, actually, that makes my combination a whole lot easier because I need to highlight the different. It's supposed to be a 3, 2, 3. Okay. Combining my x's. Combining my a's. This should have been minus 2x. Why am I not combining these correctly? Oh, yes, I am. Oh, man, Miss Gordon is really struggling. Okay, I'm going to pull out a -5, and I'm going to have an x minus a in the numerator. Okay. X minus a, 3x minus 2, 3a minus 2. All right, I found my mistakes. Thank you, guys. Okay, if I let x approach a, meaning I'm going to let this term become a, then I have -5 over 3a minus 2 squared. All right. Is that what you guys got? Wonderful. See, it told you it's going to be cute. F prime at A. Okay, so.
We got just -5 for the H method.
No, you have to get some. It's not going to be one term. Yeah, when you do a stacked fraction, you got to multiply the top and the bottom. So both methods get you middle terms. And then honestly, I made the same mistake that I see my students make, right? In this expansion term, we have to be very careful about distributing negatives and making sure that we're very focused on doing one thing at a time. Whenever I do the expansion part, I do nothing in my head. I write everything down because then it's easier to catch your mistakes, right? Yes, ma'am.
I had a question. Like you found FA in this question, but the question asked FX. So if an examiner test we write FA instead of FX, uh, like uh, so will the marks be awarded?
No. Yeah, I mean, yes, sorry. F prime is a general derivative. I used A to differentiate between my secondary points, like the point Q, and my original point, the point P. But I did not use any values. So I'm using A as a placeholder for the point of interest. So when you use the limit h goes to 0 method, because h goes to 0, your point of interest is a general x. Here it's a general A, but remember, letters are just representations. So it doesn't actually matter what you call it because this is still a general derivative. This is not a specific derivative at a point. I can put any value for A and find the derivative at that point. Does that make sense? So this method, because I'm using two x values, I have to call them different letters. With the H method, I only have one x value, so I can maintain the x, the letter x, the variable x. Okay, this was a bit ugly, but doable. Are we comfortable to move on to the second or the third example or fourth example, I guess? Okay, here is where you need to understand the definition and the idea of a derivative. We are given a sketch of the function f. Here it is. It's this loopity-loop thing. Okay, when we are looking at derivatives, we are looking at tangents at any given point. So the first thing I'm going to do is I'm going to identify where are the peaks and valleys of my graph. So on the original, here are the peaks and valleys. Okay, where or what is the derivative at the bottom of a graph or the top of a graph? It's 0, right? So f prime of x at a peak or valley is 0, because that is where our graph is changing directions. If you think of a ball being thrown up into the air, we model that with a quadratic. And when it stops and comes back down, that is the peak of that graph. So the derivative, the velocity of a falling object, is 0 at the top of the arch, right? So when I go to draw the velocity function or the rate of change function or the derivative function, the peaks and valleys represent where the graph is 0. In other words, they become the x-intercepts of the derivative graph. So the derivative is 0 at the point 1. It is 0 at the point, oh, no, I wrote that wrong, 1/2. It's 0 at 1/2. It is 0 just before 2. It is 0 at 3.5. Okay, so at the peaks and valleys, these represent where my velocity is 0. Now let's talk about what is happening between the peaks and valleys. So let's focus on this interval here. What is the slope of the points in between the first two zeros? Positive or negative? Positive. So between here, I am going to have some kind of positive graph, positive y values. I'm just going to put the plus sign in. Okay, between the second and third, if I were to draw a tangent line, what is the sign on those? Negative. So that means between the second and third zeros, my graph will be negative. And then after the last one, hopefully you can see, no matter where I am on the graph, the slope of the tangent is positive after the fact. So when we are sketching the derivative, we are sketching the values of the slope. So I'm going to write that down in maybe red so it's very aggressive. Okay? We are sketching the value of the slope. Okay? So when I go to make my graph here on the f prime side, here's f prime, it's going to have positive values between the zeros, negative values between the next zeros, and then positive values after. Okay, so it's kind of an offset graph where the original graph is going upwards. We have a loop. Where the original graph has a peak or valley, we have a 0, right? Was that what to me?
No.
Oh, you're doing something different. Okay. Any questions about this? Do we understand this concept? Here's your test question. You need to be able to identify and sketch a graph from an original function. Okay, so example 4 is your test question. Okay, other different ways we can use our notation. So if we have a function y equals f of x, another way that we can show the derivative is dy by dx. You can think of this this came from, whoopsie, delta y, change in y over change in x, right? Delta is the Greek letter, a letter D. So this is saying that we are differentiating the function y with respect to the function or to the letter x or the variable x. Okay, so we can have different, oopsie, that was supposed to be a highlighter. Here's another way that you can see it. D by dx. This means differentiate with respect to the x variable. Okay, because you could have an implicit, you guys remember implicit equations from, I don't even know where you'd get them from. If I have the circle equation, x squared plus y squared equals r squared, do we know that equation? Okay, so if I take a d by dr, I could say take the derivative of r with respect to x, or I could say take the derivative of r with respect to y, because r depends on both x and y. Okay, so this notation is just telling you which variable to do the derivative with. Okay, so this is just a little side note. We don't need to keep this. Okay, so then these are the examples that we talked about, or that we did. I think this was example 1. The f prime of x. So if f of x is x squared, f prime of x is 2x. D by dx is 2x. D by dx of x squared is still 2x. These are just the same, different ways of saying the same thing. Mean the same. If we want to indicate what is the derivative at a specific point, then we draw a line next to our d by dx, and we note what value we want to replace the x value with. This means find the derivative first, then substitute your point of interest in. There's also, we call this, you're going to laugh, don't laugh, okay? This is called the big D notation. I know, so clever. The big D notation. Capital D is also saying the differentiation operator. If you have a capital D sub x, this is to identify that you want to take it with respect to x. If you only have one variable, you don't need the sub notation. But like we saw with the equation of the circle, you could have multiple different variables into one. So all of these are different ways of saying the same thing. Okay? A function is differentiable only if f prime of a exists. What's f prime? What is f prime?
If prime of a exists, if the limit at a exists?
No. What is the definition of f prime?
The derivative.
The derivative. Which is, and what's another way of saying that? The slope of the tangent. So the function is differentiable if the derivative exists at that point. Because as we saw with piecewise functions, it could exist, the function could exist, but it does not mean it's differentiable at all points, right? An example is if you have an asymptote. You can't differentiate at that point because there's an asymptote there, okay? So on open intervals, if it is differentiable on open intervals or from a point to infinity, then it is differentiable at every number in the interval, but not necessarily at the end points. Okay, so if you have a function that exists, let's say from 2 to 118, I don't know, I'm just making this up. You can say that between 2 and 18 it's differentiable, but you cannot say that it's differentiable at 118 or at 2. Everywhere in between it's fine, but not at the end points. And it's a similar argument as if we included the endpoints. You can say the same thing. It's differentiable everywhere in between, but at the endpoints is not necessarily differentiable. That's, we need to see what the function is before we can say that. Okay? But within the interval, then we can talk about it. Here's a great example. Can you remind me, what does this function look like? Oh dear. It looks like a V, yes. Where did that line go? It disappeared. Magic trick. Woohoo! Okay. I don't know, I drew something and it disappeared. Yeah, just like that. What the heck? What is going on? Draw. What are you doing? Draw. No, draw with stylus. Like that. Yes. Close. Go away. How do I make this thing go away? Thank you. I vowed all my life that I would never, ever have an iPad. And here I am with an iPad and it's fighting me. Okay. Let me do it with this. Maybe it just doesn't like the pencil. I'll do it with the pen. All right. Seems to be okay with the pen. The absolute value function is a V-shaped function with the arms extending to in both directions.
It's differentiable, but it's not gonna have it both.
I have a question for you. What is the domain? All reals. Is it continuous? How do you know? What's the definition? You're all saying the right things, but how can I test it? The line test tells me if it's a function. I know it's a function, but is it a continuous function? Yes. Can you draw it with your pen without taking your pen off the graph? Boom. Oh, man. What is it doing here? Give it back. Stop erasing things without my permission. Draw, draw. I did not leave the graph. It is continuous. Yes. Okay. Next thing I'm going to ask you. What is the value of the slope? And value meaning, actually, you could probably tell me the value. What is the slope at this point? Positive what? Oh, not infinity. Positive 1, because, right? y1, x1, y1, 1, 1, 2, 2, 3, 3. It's just positive 1. So the slope at this point is 1. What's the slope here? What's the slope here? No.
The slope is -1. Wait, no, where? At the 0 point?
We can say, oh, go away, that the slope, oh my gosh, here we go. Slope of x equals -1 for x less than 0. We can say the slope of the tangent is +1 for x greater than 0. I'm going to explain this kind of visually.
Oh, I understand.
If you have a sharp point, a corner, versus, why won't it let me scroll to the left here? There we go. If you have a curve, then at every point in the curve, you have a distinctly unique tangent. If you have something like this, you have unique tangents here, here, and here. But at the top, when you have a sharp peak, you could, in theory, draw a tangent like this, or like this, or like this, and it doesn't really matter because it's touching the corner at one point. So we have a graph that has a tangent, in theory, but it's not a distinct one. And so when you have a corner, it is not differentiable on the corner. Okay, it does not exist. All right. So we cannot differentiate. I'm just going to call it diff at a corner because the slope that you would get at a corner is not unique. Yes. Differentiate, so means drawing a unique tangent line. Right? When we differentiate, we're drawing a unique tangent line and finding the slope. Here, I can differentiate. The slopes will be unique at every single point. But on the corner, that is not the case. So this is a non-differentiable point. So here's the catch. It is in bold. If f is differentiable at A, then AF has to be continuous at A. However, the opposite is not true. Because as we can see, F is continuous at 0. I can draw this, go through 0 without lifting my pen, but I cannot differentiate at 0. Does that make sense? Okay. So one is true, makes the other true, but not the other way around, right? Differentiable means it's continuous, but if it's continuous, not necessarily differentiable. Oh, look, I was supposed to draw it down here. Haha. No, it doesn't know things. This is not a sentient iPad. Okay, that is our lesson for today. Please note your homework. Questions? Yes, sir.
Do you have the answer for the challenge question?
I do, yes.
Can we, have you already done it?
Yeah, I don't know. I have no idea if it's right. Look at his phone.
I haven't done it.